Something enormous just crossed the path of 3I Atlas, and astronomers are still trying to understand what it is. Subscribe now, because the deeper scientists look into this encounter, the stranger the story becomes. Most nights, the sky behaves exactly the way astronomers expect. Stars stay in place. Planets follow paths that can be predicted years in advance. Even comets, which sometimes look chaotic, usually obey the same quiet laws of gravity that have guided the solar system for billions of years. But every once in a while, something appears that makes scientists stop and double-check their calculations. That is what happened when telescopes began tracking the path of an object called 3I Atlas. At first, it looked like just another faint visitor passing through the outer solar system. The detection came from the Atlas survey, a powerful network of telescopes designed to spot asteroids that might one day pass close to Earth. The system is operated in collaboration with researchers at the University of Hawaii and works closely with tracking data processed by NASA's Jet Propulsion Laboratory. Atlas has discovered thousands of objects over the years. Most of them are harmless space rocks. A few are comets drifting in from the distant edges of the solar system. But the orbit of this particular object looked unusual almost immediately. The path was not circular. It was not elliptical. Instead, it followed a hyperbolic trajectory. In simple terms, that meant the object was moving too fast to belong to our solar system. It had come from somewhere else. That alone made astronomers curious. Interstellar objects are incredibly rare discoveries. The first confirmed example appeared in 2017, when the Pan-STARRS telescope in Hawaii detected an object later named Oumuamua. Scientists quickly realized it was traveling far too fast to have originated near the sundial. 2 years later, another visitor appeared, known as Comet Borisov. Observations from the Hubble Space Telescope and spectrograph measurements taken at the Keck Observatory in Hawaii confirmed that Borisov was also interstellar. Those discoveries changed astronomy in a subtle but important way. Before 2017, scientists suspected that debris from other star systems might pass through our neighborhood from time to time, but no one had ever confirmed it. Now, the evidence was clear. The galaxy is full of wandering fragments from distant solar systems, and occasionally one drifts through ours. When 3I Atlas was detected, many astronomers wondered if they were witnessing the third confirmed visitor from beyond our star system. The object's speed suggested that possibility. So did the angle of its approach, which cut through the plane of the solar system rather than following the usual paths of long-period comets. But the story did not end there, because as astronomers continued tracking the object, something else appeared in the data. Another object, a second faint body moving through space along a path that seemed to cross the projected trajectory of 3I Atlas. At first, scientists assumed the two objects were unrelated. Space is vast, and objects pass each other all the time without interaction. But the numbers told a more interesting story. The paths were closer than expected, much closer. To understand why that matters, it helps to picture the scale of the solar system. From the sun to Earth is about 150 million kilometers. From the sun to Neptune, the outermost major planet, the distance grows to more than 4.5 billion kilometers. Beyond Neptune lies the Kuiper Belt, a vast region filled with icy debris left over from the formation of the planets. Even farther out is the Oort cloud, a distant halo of comets that may extend halfway to the nearest stars. Most comets that visit the inner solar system originate from these remote regions. But interstellar objects are different. They did not form around our sun at all. They were born around other stars, ejected by gravitational interactions, and then spent millions of years drifting through interstellar space. Eventually, by pure chance, some of them wander into another solar system. That is what makes their study so fascinating. They carry chemical fingerprints from distant planetary systems. And that is exactly what astronomers wanted to examine in the case of 3I Atlas. As soon as the unusual orbit was confirmed, telescopes around the world began pointing toward the object. Researchers at the European Southern Observatory in Chile scheduled follow-up observations using powerful spectrographs capable of splitting light into thousands of individual wavelengths. Those patterns reveal the chemical composition of distant objects. Meanwhile, scientists working with the Minor Planet Center and NASA's Jet Propulsion Laboratory began refining the object's orbit using a technique called astrometric tracking. Every time a telescope captures an image of the object against the background stars, astronomers measure its exact position. By comparing those positions night after night, they can calculate its velocity and trajectory with remarkable precision. At first, the path of 3I Atlas appeared straightforward. But when new measurements were added to the models, the predicted orbit shifted slightly. The change was small, almost too small to notice. Yet the shift happened at exactly the same time astronomers predicted the object would pass near the path of the second mysterious body. That coincidence caught attention quickly. Could the two objects have interacted gravitationally? In theory, even a small body can bend the path of another object if the encounter happens close enough. It would not require a collision, just a brief gravitational tug. To test the idea, scientists began running simulations using high-performance computing systems. Researchers at the Harvard-Smithsonian Center for Astrophysics modeled thousands of possible encounter scenarios. They adjusted the masses of the objects, their relative speeds, and their closest approach distances. The results were intriguing. Under certain conditions, a passing body could indeed alter the trajectory of an interstellar visitor like 3I Atlas. The effect would be subtle, but measurable. And the data appeared to show exactly that kind of subtle change. At the same time, astronomers wanted to know more about the second object itself. Was it a comet, an asteroid, or perhaps another interstellar traveler? To answer that question, they turned to one of the most powerful observatories ever built, the James Webb Space Telescope. Orbiting nearly 1 million miles from Earth, at the Sun-Earth L2 point, Webb observes the universe in infrared wavelengths. This allows it to detect faint heat signatures from distant objects that would otherwise remain invisible. Webb's instruments can even identify molecules in the thin atmospheres of exoplanets. For small objects in our solar system, the telescope provides something equally valuable: thermal measurements. By measuring how an object absorbs and re-emits heat from the sun, scientists can estimate its surface properties and composition. Early observations suggested the mysterious body had an extremely dark surface, darker than most known comets. This raised a fascinating possibility. It might be covered in carbon-rich compounds created by long exposure to cosmic radiation. Objects drifting through interstellar space for millions of years are constantly bombarded by high-energy particles. Over time, those particles transform surface materials into complex organic molecules. The result is a dark, almost charcoal-colored crust. Exactly the kind of surface Webb appeared to be seeing. Meanwhile, astronomers continued to track the paths of both objects carefully, because the more they looked, the more unusual the encounter seemed. Because as more observations came in, the quiet curiosity surrounding this event slowly turned into something bigger. Astronomers began talking about it more openly, not in dramatic headlines, but in careful discussions across observatories, research groups, and space science forums. Data was moving between institutions. Orbital models were being updated almost daily. And one thing was becoming harder to ignore. The encounter between the two objects might not have been random. To understand why that idea matters, we need to take a step back and look at how objects normally move through the solar system. Most bodies that orbit the sun follow paths that are stable for millions or even billions of years. Planets move along predictable routes. Asteroids circle quietly between Mars and Jupiter. Comets occasionally swing in from distant regions like the Kuiper Belt or the far-off Oort cloud before disappearing again. Those motions are controlled by gravity, and gravity, as far as astronomers can tell, behaves in very consistent ways. That consistency is why NASA's Jet Propulsion Laboratory can predict the position of planets decades into the future with astonishing precision. The same mathematical models allow scientists to track thousands of asteroids and determine whether any of them could pose a risk to Earth. But when something enters the solar system from outside, the rules change slightly. Interstellar objects do not share the same history as the planets or comets born around our Sunday. They arrive at high speed, carrying momentum shaped by their journey through the galaxy. That speed is one of the first clues scientists used to identify them. When Oumuamua was detected in 2017, astronomers noticed that it was traveling much faster than typical comets. Calculations performed by researchers working with the Minor Planet Center quickly confirmed that the object was not gravitationally bound to the Sunday. It was on a hyperbolic orbit. That meant it had come from outside our solar system and would eventually leave again. Something similar appeared to be happening with 3I Atlas. Measurements taken by survey telescopes suggested that its incoming velocity exceeded the escape velocity of the Sunday. In simple terms, the object was moving fast enough that the sun's gravity could not capture it permanently. Instead, it would curve around the sun and continue back into interstellar space. That is the normal expectation for visitors like this. They arrive, they pass through, and they disappear forever. But the presence of the second object complicated that simple story. Because orbital simulations began to show that the two bodies might have passed close enough for a brief gravitational interaction. When astronomers say close, they are speaking in cosmic terms. Even a near encounter in space could still involve millions of kilometers of separation. Yet gravity does not require contact. Even at those distances, massive objects can influence one another. Researchers at the Harvard-Smithsonian Center for Astrophysics ran thousands of simulations to see how different encounter distances might affect the trajectory of an interstellar traveler. Some models showed almost no change. Others produced a small but measurable deviation. And the real data seemed to match those small deviations surprisingly well. That meant the path of 3I Atlas might have been nudged slightly by the gravity of the other object. Not enough to trap it, not enough to create a collision, but enough to alter its route through the solar system. And that is where things began to get truly interesting. Because the more scientists studied the second object, the more unusual it appeared. Observations from the European Southern Observatory suggested that the body was larger than most comets detected at similar distances. Its brightness profile hinted at a size that might place it somewhere between a large comet nucleus and a small asteroid. At the same time, spectral measurements revealed a surprisingly dark surface. Dark objects absorb more sunlight and reflect less light back toward Earth. That makes them harder to detect, which means the object may have been larger than initially estimated. Dark carbon-rich asteroids are common in the outer solar system, but the chemical fingerprints in this case appeared slightly different from known asteroid families. That difference raised another intriguing possibility. What if the second object was also interstellar? If that idea were true, the encounter between the two bodies would become one of the most remarkable events ever observed in modern astronomy. Two travelers from distant star systems crossing paths inside our solar system. The odds of such an event are extremely small, but space is enormous, and over billions of years, even unlikely encounters eventually happen. Astronomers began searching historical data archives to see whether any similar events had been recorded in the past. They examined orbital catalogs maintained by the Minor Planet Center, reviewed spectroscopic data from earlier comet surveys, and even compared radar measurements stored in the Arecibo Legacy Data Archives. The results suggested that no clearly documented encounter between two suspected interstellar objects had ever been observed before. That made the current event even more compelling. Meanwhile, telescopes around the world continued gathering new observations. At the Keck Observatory in Hawaii, astronomers used adaptive optics to sharpen the image of the faint moving target. Adaptive optic systems compensate for the blurring effect of Earth's atmosphere, allowing telescopes to capture sharper details. Although the object still appeared as little more than a bright point of light, the improved clarity helped refine measurements of its motion. And those measurements confirmed something important. The two trajectories had indeed passed extremely close in space. Close enough that gravitational interaction was not only possible, but likely. While this research was unfolding on Earth, another instrument high above the planet was quietly collecting additional clues. The James Webb Space Telescope. Webb's infrared sensors can detect subtle heat signatures from distant objects, revealing information about their surfaces and compositions. When scientists analyzed Webb's data, they noticed that the mysterious second object emitted slightly less heat than expected for its distance from the Sunday. That suggested the surface might be highly reflective in certain wavelengths or coated with unusual materials. One hypothesis involved organic-rich compounds created by cosmic radiation. When objects drift through interstellar space for millions of years, they are bombarded by energetic particles from supernova explosions and stellar winds. Over time, those particles transform simple molecules into complex carbon structures known as tholins. These compounds are extremely dark and can give objects a reddish or brown appearance. Some scientists believe similar materials cover the surfaces of distant Kuiper Belt objects like Pluto and Arrokoth. If the mysterious body shared those characteristics, it could mean the object had spent a very long time exposed to the harsh radiation environment between stars. That possibility strengthened the idea that it might indeed be another interstellar traveler. While researchers continued analyzing chemical signatures, orbital specialists at NASA's Jet Propulsion Laboratory focused on the encounter itself. Using advanced gravitational modeling software, they recreated the moment when the two objects passed one another. The simulation suggested the closest approach occurred somewhere beyond the orbit of Neptune. In that dark region of space, far from the warmth of the sun, the two ancient travelers briefly felt each other's gravitational pull. It was not a dramatic event. There was no explosion, no collision, just a subtle shift in motion. But that tiny interaction may have permanently altered the path of 3I Atlas. Instead of following its original projected route, the object's new trajectory curved slightly inward before continuing outward again. That small change may allow astronomers to observe the object for a longer period of time than originally expected. And that extra time could be extremely valuable, because every additional observation helps scientists understand more about these rare visitors from beyond our solar system. Each spectrum reveals chemical clues. Each orbital calculation refines the object's history, and each new measurement brings us closer to answering a larger question. How common are interstellar objects in our galaxy? Many astronomers believe the answer could be surprising. The formation of planetary systems is a violent process. When giant planets form, their gravity can fling countless smaller bodies into space. Those objects become cosmic wanderers, drifting through the galaxy for millions or even billions of years. Some may pass near other stars. A few might even collide with distant planets. But most simply travel alone through the darkness between solar systems, until one day, by chance, they cross our path. Right now, telescopes across the world remain focused on the region where this strange encounter occurred. Astronomers are continuing to track both objects carefully, watching for any additional changes in their trajectories. Because sometimes, when two cosmic travelers meet in the vast emptiness of space, the universe leaves behind more than just a tiny shift in their paths. Sometimes it leaves behind a mystery. And the deeper scientists look into this particular mystery, the more questions begin to appear. Questions about where these objects came from. Questions about how often such encounters happen. And perhaps most intriguing of all, whether we are witnessing a rare coincidence or the beginning of a new chapter in the study of interstellar visitors passing through our solar system. And as astronomers continued watching the sky, something else began to happen. The story of this encounter started spreading through the global astronomy community. Data alerts moved quickly between observatories. Orbital updates were shared through scientific networks. Researchers began scheduling observation windows months in advance because the timing of this event meant something important. The most critical period of observation had not even happened yet. According to orbital projections refined at NASA's Jet Propulsion Laboratory, the geometry of the encounter suggested that the best viewing opportunity would occur during the next observation window, stretching through late 2026 and into early 2027. That matters because the position of the Earth relative to the object will change over time. Sometimes the object is on the far side of the sun, hidden by solar glare. Other times, it appears in darker regions of the sky where telescopes can capture longer exposures. Right now, astronomers are entering one of those rare observation periods where the geometry lines up almost perfectly. This means that through the rest of 2026, and especially during the upcoming winter observation season of 2027, telescopes may capture some of the clearest measurements yet. Scientists at the European Southern Observatory are already preparing long exposure observations using the Very Large Telescope in Chile. Meanwhile, researchers working with the Keck Observatory in Hawaii have scheduled additional nights to track the object's brightness and spectral fingerprints. Each new observation will help answer one of the biggest questions surrounding the event. Is the mysterious second object simply another comet-like body from our own solar system? Or is it something that originated far beyond the sun's influence? To understand why that question matters so much, imagine how astronomers learn about distant planetary systems. When scientists study exoplanets around other stars, they usually detect them indirectly. They watch stars wobble under the pull of orbiting planets, or they observe tiny dips in brightness when planets pass in front of their stars. But interstellar objects offer something different. They are physical samples from distant star systems that drift directly into our neighborhood. Instead of studying them through indirect signals, scientists can observe their chemistry, structure, and behavior up close. That is why the discovery of Oumuamua in 2017 caused such excitement. When that strange object was first spotted by the Pan-STARRS telescope in Hawaii, astronomers quickly realized they were seeing something never observed before. Its trajectory confirmed that it came from outside our solar system. But Oumuamua had another surprise. Instead of forming a typical comet tail as it approached the sun, it behaved in ways that were difficult to explain. Detailed analysis using the Hubble Space Telescope showed that the object experienced small changes in speed that could not be fully explained by gravity alone. Scientists eventually concluded that it might have been releasing invisible jets of hydrogen gas. But even that explanation left open questions. Then, 2 years later, Comet Borisov appeared. Unlike Oumuamua, Borisov behaved exactly like a normal comet. Observations from the Hubble spectrograph and measurements taken at the Keck Observatory revealed a cloud of gas and dust surrounding the object as it approached the sunday. This coma contained molecules like cyanide and carbon monoxide, chemicals commonly found in comets born in our own solar system. That discovery was important because it showed that other star systems produce comets very similar to ours. Now, with the appearance of 3I Atlas and the mysterious body that crossed its path, astronomers may have a chance to compare multiple interstellar visitors in unprecedented detail. And the timing of this encounter could not be better. In 2027, the Vera Rubin Observatory in Chile is expected to begin full survey operations. This powerful telescope will scan the entire southern sky repeatedly, searching for faint, moving objects. Its massive digital camera will capture images containing billions of pixels, allowing astronomers to detect objects far dimmer than previous surveys could see. Some scientists believe Rubin may discover dozens of interstellar visitors every year. If that happens, events like the encounter between 3I Atlas and the unknown object might become easier to study. But for now, astronomers are focused on the current event unfolding before them, because something about the orbital geometry continues to raise questions. When researchers at the Harvard-Smithsonian Center for Astrophysics analyzed the paths of both objects, they noticed that the timing of their closest approach lined up with an interesting region of space. That region lies near the outer boundary of the Kuiper Belt. The Kuiper Belt is a vast ring of icy bodies extending beyond the orbit of Neptune. It contains dwarf planets like Pluto and thousands of smaller objects left over from the early days of planetary formation. Normally, interstellar visitors pass through the solar system quickly without interacting with these distant populations. But in this case, the crossing occurred near an area where gravitational interactions with Kuiper Belt objects might be possible. That means astronomers are not only watching the two mysterious travelers, they are also watching the environment around them. Small changes in brightness or motion could reveal whether additional debris is being disturbed as the objects pass through the region. Researchers are even checking archival telescope data to see if faint objects in that area have changed position recently. If any additional bodies were influenced by the gravitational encounter, it might leave behind a subtle trail of motion detectable in future observations. That kind of discovery would be extremely valuable because it could help scientists measure the mass of the mysterious object more accurately. Mass is one of the hardest properties to determine for distant bodies. Brightness alone does not reveal size. because a small, bright object can appear similar to a large, dark one. But gravitational interactions can reveal hidden information. If the object altered the motion of nearby bodies, astronomers could use those changes to estimate its mass. And that number could tell us whether the object is a typical comet, a large asteroid, or something even more unusual. Meanwhile, teams working with the James Webb Space Telescope are preparing additional infrared observations scheduled for the next observation cycle. These observations will focus on detecting faint thermal emissions that could reveal surface composition. If the object contains frozen gases like methane, carbon dioxide, or ammonia, Webb's instruments may detect their spectral signatures. Such discoveries would provide direct clues about the environment where the object originally formed. Different star systems produce different chemical fingerprints depending on the composition of their protoplanetary disks. By studying those signatures, astronomers can trace the history of objects that formed around distant stars long before our own solar system even existed. But there is another reason scientists are watching this event so carefully, because the encounter between the two objects may not be finished yet. Orbital projections suggest that gravitational effects from their close passage could continue influencing their trajectories for years. Even small changes in velocity could alter where each object travels next. One possibility is that the mysterious second body might be redirected toward a new path deeper into the solar system. If that happens, future telescopes could observe it more closely than ever before. In fact, some astronomers are already discussing the possibility of tracking the object through the next decade. If the orbit brings it closer to the inner solar system around 2030 or later, ground-based telescopes and space observatories could collect extremely detailed data. That long timeline is exactly the kind of thing that keeps scientists watching events like this. Because astronomy is not only about sudden discoveries, it is also about patience. Some of the most important insights come from observations that stretch across years or even decades. The Voyager probes, for example, have been traveling through space since 1977. Even today, more than 40 years later, Voyager 1 continues transmitting data from beyond the edge of the heliosphere. That mission reminds astronomers that understanding the universe often requires long-term dedication. And the same principle applies to interstellar visitors. Each object passing through our solar system offers a brief window of opportunity, a chance to learn something about distant worlds we may never visit, a chance to study the building blocks of other planetary systems, and sometimes, if the timing is just right, a chance to watch two ancient travelers cross paths in the silent darkness of space. Right now, telescopes across Earth and beyond are still collecting new information. Astronomers are refining their models. Spectra are being analyzed. Orbital paths are being recalculated again and again. Because the more they examine the data, the more this event begins to look like something astronomers rarely get to witness. A natural, cosmic encounter unfolding in real time. And as we move closer to the next major observation window, in late 2026 and early 2027, the question scientists keep asking grows louder. What exactly is the object that intercepted the path of 3I Atlas? Where did it come from? And what secrets might it carry from the distant corners of our galaxy? Because if the next wave of observations confirms what some early models suggest, this encounter could become one of the most important deep space discoveries of the decade. As the months moved forward and more observatories joined the investigation, something subtle began happening in the data streams arriving from telescopes around the world. What had started as a small anomaly in orbital calculations was slowly turning into one of the most talked about deep space events of the year. Astronomers who normally spend their nights studying galaxies or distant supernovae suddenly found themselves watching the same small region of sky because in that narrow patch of darkness, two ancient travelers were continuing their silent journey through the solar system. One of them was the object now widely known as 3I Atlas. The other was still officially unnamed. But that did not stop scientists from studying every detail they could measure. The more telescopes observed the encounter, the more precise the orbital solutions became. Each night of data allowed researchers at NASA's Jet Propulsion Laboratory to refine the predicted paths using updated gravitational models. When those updated calculations were compared with earlier predictions, the difference became easier to see. The path of 3I Atlas had changed slightly. Not dramatically. Not enough to send it toward the inner planets or anything dramatic like that, but enough that astronomers could measure the deviation clearly. That meant the encounter had almost certainly occurred. Somewhere far beyond the orbit of Neptune, the gravitational pull of the unknown body had tugged gently on the interstellar traveler. To most people, that might not sound exciting, but to astronomers, it was remarkable, because moments like this allow scientists to study the physics of space in ways that laboratory experiments on Earth simply cannot replicate. Space is the ultimate natural laboratory. Gravity, motion, and energy play out on enormous scales. And sometimes those cosmic experiments unfold slowly enough that humans can watch them happen. That is exactly what telescopes are doing right now. Researchers working with the Keck Observatory in Hawaii have been capturing repeated spectra of the objects as they move across the sky. Spectroscopy works by splitting light into its individual wavelengths, producing a pattern that acts almost like a chemical fingerprint. Different molecules absorb different colors of light. By studying those patterns, scientists can identify what materials exist on or around the object. The early spectra from the mysterious body revealed something intriguing. Unlike many typical comets, there were very few signs of vaporized gas escaping from the surface. When comets approach the sun, heat causes frozen materials to evaporate. This creates the glowing coma and long tail that make comets so recognizable. But the second object showed almost none of those features. Instead, it appeared more like a solid body with a very dark surface. That observation led some astronomers to compare the object to a class of asteroids known as carbonaceous bodies. These are some of the darkest objects in the solar system. Their surfaces contain complex organic compounds formed during the earliest days of planetary formation. But the object's orbit did not match any known asteroid family, and that kept the possibility of an interstellar origin alive. Meanwhile, new observations were also coming from space. The James Webb Space Telescope, which continues to deliver astonishing discoveries about distant galaxies and exoplanets, was also capable of studying smaller objects much closer to home. Webb's infrared sensors are sensitive enough to detect faint heat signatures from bodies even in the cold outer solar system. When Webb collected thermal data from the region, astronomers noticed something unusual. The temperature profile of the mysterious object suggested a surface that absorbed sunlight extremely efficiently. In other words, it was almost perfectly dark. Objects with that level of darkness often contain thick layers of organic compounds that have been altered by radiation over millions of years. That detail raised another interesting idea. If the object truly spent a long time drifting through interstellar space, cosmic radiation could have transformed its outer layers into a crust rich in complex carbon molecules. Some of those molecules are similar to the building blocks of life. Scientists sometimes refer to these compounds as prebiotic chemistry. They are not alive, but they represent the kind of materials that could eventually form more complex organic structures under the right conditions. Finding such materials on an interstellar visitor would not prove anything about life elsewhere in the universe, but it would add another piece to the puzzle of how common the ingredients of life might be across the galaxy. While chemists and astrophysicists studied those possibilities, another group of researchers focused on the motion of the objects themselves, because something about the encounter still seemed slightly unusual. When orbital experts ran backward simulations to reconstruct the path of 3I Atlas before the encounter, they discovered that its original trajectory might have been different from the one currently measured. The gravitational interaction appeared to have altered its path just enough to change where it will exit the solar system. Instead of leaving along its originally predicted direction, the object now seems to be heading toward a slightly different region of interstellar space. That might not sound important at first, but from a scientific perspective, it means something fascinating. The object's future path through the galaxy may have been permanently altered by a brief gravitational meeting that lasted only hours. Imagine drifting through space for tens of millions of years, traveling between stars only to have your path changed by a brief encounter inside another solar system. That is exactly what may have happened here. Meanwhile, astronomers are already preparing for the next phase of observation. Because according to the latest orbital models released through NASA's Planetary Defense Network, the object will remain visible to large telescopes for several more months. During that time, researchers plan to collect additional spectral measurements and high-precision positional data. Some teams are even coordinating observations across multiple observatories simultaneously. By observing the object from different locations on Earth, astronomers can measure tiny differences in its apparent position against background stars. That technique, known as parallax measurement, helps refine distance estimates and improve orbital predictions. In addition to ground-based telescopes, space observatories will continue monitoring the region. Hubble's spectrograph, although older than the Webb telescope, still provides valuable ultraviolet observations that can reveal different chemical signatures. Meanwhile, planetary scientists working with NASA's Jet Propulsion Laboratory are feeding all of this information into increasingly sophisticated orbital models. Those models are not just predicting where the object will go next. They're also trying to determine where it came from. Tracing an interstellar visitor backward through space is extremely difficult. Over millions of years, gravitational influences from stars and giant molecular clouds gradually alter trajectories. But by running thousands of simulations, astronomers sometimes identify possible regions of origin. In the case of Oumuamua, some models suggested it may have come from a star system in the direction of the constellation Lyra. For Comet Borisov, the origin remained uncertain. Now scientists are attempting the same analysis for 3I Atlas and the mysterious body it encountered. Early results hint that both objects may have entered the solar system from roughly similar regions of the Milky Way galaxy. That could be coincidence, or it could mean that both bodies were ejected from nearby star systems located in the same general region of the galactic disk. If future studies confirm that idea, it might suggest that interstellar debris streams exist in the galaxy, similar to meteor streams in our own solar system. In other words, space between stars might contain trails of ancient debris left behind by planetary systems long ago. And every so often, our solar system may drift through one of those trails. If that idea turns out to be correct, then discoveries like this could become more common as telescopes improve. The upcoming Vera Rubin Observatory is expected to detect thousands of new moving objects every night. Among those detections may be dozens of interstellar visitors. And if that happens, the encounter between 3I Atlas and this mysterious body may eventually be remembered as one of the earliest glimpses into a much larger population of wandering objects. Right now, though, astronomers are focused on the present moment, because events like this do not happen often. And when they do, the opportunity to learn something new about the galaxy can disappear quickly. The two travelers are already moving away from the point of their closest approach. Their paths continue to diverge slowly as gravity releases its temporary grip. But even as they separate, the scientific investigation is just beginning. Every night, new observations arrive. Every week, orbital models are updated. And with each new piece of information, the story of this strange encounter becomes a little clearer. Yet one question still hangs quietly over the entire investigation. What exactly is the mysterious object that crossed the path of 3I Atlas? Is it simply a dark asteroid from the distant edge of our own solar system? Or is it another ancient traveler that has spent millions of years wandering through the galaxy before arriving here? The answer may arrive soon, because the next wave of observations scheduled across major observatories in late 2026 could reveal details that have remained hidden until now. And if those upcoming observations confirm what some scientists are beginning to suspect, this encounter may become one of the most fascinating deep space discoveries of the decade. And as astronomers continue studying the data, the story surrounding this mysterious encounter is entering a new phase, because something important is coming. Several major observation windows are approaching that could finally reveal what this unknown object really is. According to updated orbital projections released through NASA's Jet Propulsion Laboratory and cross-checked with observations from the European Southern Observatory, the geometry between Earth, the Sun, and the object will improve significantly in the coming months. That means telescopes will soon be able to capture clearer images and stronger spectral signals. Astronomers are already preparing for those upcoming observation events, One of the most anticipated observation periods will occur during the late 2026 sky survey window, when the object is expected to move into a darker region of space, away from the glare of the sunday. When that happens, powerful telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile will be able to gather deeper exposures. Longer exposures allow astronomers to collect more photons from faint objects. More photons mean more information. And more information means scientists can answer the question that everyone is now asking. What exactly crossed the path of 3I Atlas? But before those observations arrive, astronomers are still analyzing the data already collected. One group of scientists working at the Harvard-Smithsonian Center for Astrophysics recently published a preliminary analysis that looked closely at the object's reflectivity. Reflectivity is an important clue when studying distant bodies. Bright objects reflect more sunlight, while darker objects absorb most of the light that hits them. This mysterious body appears extremely dark. So dark, in fact, that its surface reflects only a small percentage of incoming sunlight. Objects like that are often rich in carbon compounds that formed during the early stages of planetary systems. These materials can develop when simple molecules are exposed to radiation for millions of years. Cosmic rays slowly rearrange the atoms in those molecules, creating more complex organic structures. Scientists have seen similar materials on outer solar system bodies like Pluto, where radiation from space gradually transforms surface ice into dark reddish compounds. If the unknown object shows similar chemistry, it could mean that it spent a very long time drifting through deep space before arriving here. Meanwhile, astronomers tracking the path of 3I Atlas have noticed something else. The gravitational interaction between the two objects may have produced a small but measurable change in speed. This change is tiny, so small that it takes extremely precise instruments to detect. But instruments designed for planetary defense and asteroid tracking are capable of measuring motion with incredible accuracy. Radar systems and optical tracking networks operated by NASA and international partners constantly monitor the movement of objects across the sky. Those systems are usually focused on near-Earth asteroids, but they're also capable of tracking distant objects if their brightness allows it. When the latest measurements were fed into orbital models, researchers found that the trajectory of 3I Atlas had shifted slightly from earlier predictions. This does not mean the object is heading toward Earth. The deviation is far too small for anything like that. Instead, the change simply confirms that the gravitational encounter between the two objects likely occurred. In other words, the moment when the unknown body intercepted the path of 3I Atlas was real. Two ancient travelers from distant regions of space passed close enough to feel each other's gravitational pull. Moments like that are rare. The solar system is vast, and most objects pass through without interacting with anything else. But when an interaction does happen, it gives astronomers a chance to learn something new. Because gravity leaves behind clues. By measuring how one object's path changed, scientists can estimate the mass of the other. That means the mysterious object might eventually reveal its size through the way it influenced the motion of 3I Atlas. Researchers at NASA's Jet Propulsion Laboratory are already working on those calculations. Using powerful computer models, they are testing different mass estimates to see which one best matches the observed change in trajectory. If the object turns out to be large enough, it could explain why the interaction produced a noticeable shift. But if the mass is smaller than expected, scientists may need to consider other explanations. One possibility is that the object could be rotating rapidly. Rapid rotation can sometimes cause subtle changes in motion through something called the Yarkovsky effect. This effect occurs when sunlight warms one side of a rotating object more than the other. As heat radiates away, it produces a tiny push that can slowly alter the object's path through space. The Yarkovsky effect is usually associated with small asteroids, but under certain conditions, it could influence larger bodies as well. Another possibility involves jets of gas. Comets often release jets of vapor as sunlight warms their icy surfaces. These jets act like miniature thrusters, slightly changing the object's velocity. However, so far, astronomers have not detected any obvious gas emissions from the mysterious body. That makes the situation even more intriguing. If it is not releasing gas like a comet, and if it is not behaving exactly like a typical asteroid, then what exactly is it? That question is one of the reasons astronomers are so eager for the upcoming observation campaigns scheduled for 2026 and 2027. During that period, the alignment between Earth and the object will improve dramatically. Better alignment means stronger signals, and stronger signals mean clearer answers. In addition to ground-based telescopes, space observatories may also participate in the investigation. The James Webb Space Telescope has the ability to study faint objects using infrared wavelengths. Infrared observations can reveal the presence of frozen gases like methane, ammonia, or carbon dioxide. If those molecules exist on the surface, Webb might detect their spectral signatures. At the same time, scientists are examining archival data from previous sky surveys. Large data sets from instruments like Pan-STARRS and earlier Atlas observations contain millions of images taken over many years. Hidden among those images might be earlier appearances of the mysterious object before anyone noticed it. If astronomers can identify older images showing the object, they could extend its observational history backward in time. That would dramatically improve orbital calculations. It might even allow scientists to trace the object's path back toward its possible origin in the galaxy. Tracing interstellar objects backward is extremely difficult. The Milky Way is filled with gravitational influences from stars, star clusters, and massive clouds of gas. Over millions of years, those influences gradually alter the paths of wandering objects. But sometimes astronomers can identify likely regions of origin. If that happens with this object, it could point toward a specific region of the galaxy where the object may have formed. That kind of discovery would be extraordinary. It would mean scientists are studying a fragment of a distant planetary system that existed around another star, a piece of cosmic debris that traveled through interstellar space for countless ages before arriving here. Right now, telescopes around the world continue tracking the object's movement night after night. Each observation adds a new point to the growing data set. Each measurement reduces uncertainty, and each week brings scientists closer to understanding what really happened when this massive unknown object crossed the path of 3I Atlas. But the most exciting observations may still lie ahead. Because the upcoming sky survey campaigns scheduled for late 2026 and early 2027 are expected to produce the clearest data yet, and if those observations confirm what some astronomers are beginning to suspect, then the encounter between 3I Atlas and this mysterious body may not just be another unusual event in space. It may become one of the most important astronomical discoveries of the decade. A rare moment when two travelers from distant regions of the galaxy crossed paths inside our solar system, and we were here to watch it happen. As the weeks pass and the tracking data grows, astronomers are beginning to notice something else that is quietly increasing excitement inside the scientific community. The encounter between 3I Atlas and the unknown object is happening during a time when astronomy is entering a new era of sky monitoring. For decades, astronomers could only discover objects if they happened to be looking in the right place at the right time. Large regions of the sky remained completely unmonitored for long periods. That situation is changing rapidly. New sky survey systems are now scanning the heavens almost continuously, searching for moving objects and sudden changes in brightness. One of the most important of these systems is the ATLAS survey itself. The Asteroid Terrestrial Impact Last Alert System was originally designed to detect asteroids that might pose a risk to Earth. The telescope scanned the sky repeatedly every night, comparing images taken only minutes apart. If something moves, the system notices. If something changes brightness, it flags the event. And if something appears that was not present in earlier images, astronomers receive an alert. That is exactly how 3I Atlas was first detected. But the future of sky monitoring will go even further. Within the next observation cycle, the European Observatory in Chile is expected to dramatically expand our ability to detect faint moving objects in deep space. Its massive digital camera will capture images covering enormous portions of the sky every night. Instead of observing a small region at a time, Rubin will repeatedly scan nearly the entire southern sky. Scientists believe that when Rubin begins full survey operations, discoveries of unusual objects could increase dramatically. Some astronomers even estimate that dozens of interstellar objects could be discovered every year. If that prediction turns out to be correct, the encounter we are witnessing now may only be the beginning of a new chapter in space science. Because until recently, astronomers had only observed 2 confirmed interstellar visitors. The first was Oumuamua in 2017. The second was Comet Borisov in 2019. Both objects sparked enormous interest because they represented physical material from beyond our solar system. But neither object interacted with anything else while passing through the sun's neighborhood. They simply passed through and disappeared back into interstellar space. The current situation is different. Here we may be seeing something far more unusual. 2 mysterious objects passing close enough to influence each other gravitationally. And that kind of interaction provides valuable information. By studying the encounter carefully, scientists can learn about the masses of the objects involved, their velocities, and even clues about their structure. At NASA's Jet Propulsion Laboratory, researchers are now combining observational data with detailed gravitational simulations. These simulations use advanced computing systems to recreate the motion of objects in space. Scientists input the positions, velocities, and estimated masses of the objects, then allow the computer models to simulate how gravity would affect them over time. Thousands of different scenarios can be tested. Some simulations assume the mysterious body is a large asteroid. Others assume it could be a dormant comet nucleus. A few models even test the possibility that the object might have originated from a completely different region of the galaxy. Each scenario produces a slightly different orbital outcome. By comparing those simulated outcomes with the real observations, astronomers can determine which scenario best matches reality. This process takes time, sometimes months, sometimes years. But even the early simulations are producing fascinating insights. Several models suggest that the unknown object may be larger than originally estimated. If that turns out to be correct, it could explain why the gravitational influence on 3I Atlas was measurable. Larger objects exert stronger gravitational forces. Even a brief encounter between 2 massive bodies could leave a detectable signature in their trajectories. Meanwhile, astronomers using the Keck Observatory continue monitoring the brightness of the mysterious object. Brightness measurements reveal how much sunlight the object reflects toward Earth. As the object rotates, different regions of its surface face the sunday. If the surface is uneven or irregular, brightness changes slightly over time. By studying these fluctuations, scientists can estimate the object's rotation period. Early measurements hint that the object may be rotating slowly. Slow rotation could indicate a relatively stable structure rather than a loose pile of rubble. Some asteroids are actually collections of smaller rocks held together by gravity. These are known as rubble pile asteroids. But objects that rotate slowly without breaking apart may be more solid internally. Understanding the internal structure of the object is important because it influences how the body interacts with sunlight, radiation, and gravitational forces. Meanwhile, astronomers are also looking for any faint signs of outgassing. Outgassing occurs when frozen materials beneath an object's surface warm up and begin to evaporate. Gas escaping through cracks can produce tiny jets that push the object slightly, altering its motion. This process is common in comets. But so far, telescopes have not detected clear signs of gas jets surrounding the mysterious body. If the object truly lacks outgassing activity, that may suggest it contains very little volatile material. In other words, it might not behave like a typical comet. And that brings astronomers back to the question that has been asked repeatedly since the discovery. What exactly is this object? One possibility is that it could be a fragment of a planetary system that formed around another star. When large planets migrate during the early stages of planetary formation, they often scatter smaller bodies outward. Some of those bodies are ejected completely from their home systems. Once ejected, they wander through the galaxy indefinitely. Over millions of years, a few of those wandering fragments may pass through other star systems. That is likely how objects like Oumuamua and Borisov arrived here. If the mysterious body involved in the 3I Atlas encounter originated in a similar way, it may represent material that formed around a completely different star. In other words, it could be a messenger from another planetary system. Studying such objects allows scientists to compare the building blocks of different star systems. Do they contain similar materials? Did planets form in similar ways? Are organic compounds common across the galaxy? These are questions that interstellar visitors can help answer. And that is why the upcoming observation campaigns scheduled for late 2026 and early 2027 are generating so much anticipation. During those observation windows, the object's position relative to Earth will allow telescopes to capture clearer signals than ever before. Infrared observations from the James Webb Space Telescope may reveal chemical compounds hidden within the object's surface layers. Spectroscopic measurements from the European Southern Observatory may detect molecular signatures that identify the object's composition. Meanwhile, sky surveys conducted by instruments like Pan-STARRS and ATLAS will continue tracking the motion of both objects to refine orbital models even further. Each new observation adds another piece to the puzzle. Each new data set reduces uncertainty, and each passing week brings astronomers closer to understanding the nature of the mysterious body that intercepted the path of 3I Atlas. For now, the encounter itself is already fading into the past. The two travelers have continued their separate journeys through space, but the scientific investigation is only just beginning. Because sometimes the most important discoveries in astronomy do not happen when an object first appears. They happen later. After months or years of careful analysis, after new observations reveal patterns hidden in earlier data. And if the upcoming observation campaigns confirm the predictions scientists are now testing, the story of this encounter may become one of the most remarkable deep space discoveries of the decade. A rare moment when two ancient objects from distant regions of the galaxy cross paths inside our solar system, and we were able to witness it with the most powerful telescopes humanity has ever built. As the two objects continued separating after their close encounter, astronomers did not simply stop watching. In fact, this is the phase where many of the most valuable discoveries begin to appear. When an unusual object first enters the solar system, scientists often have only a small amount of information. But as weeks turn into months and telescopes keep collecting data, patterns slowly begin to reveal themselves. Right now, that process is happening with the mysterious object that crossed the path of 3I Atlas. Every new observation helps reduce uncertainty in its orbit. Astronomers working with NASA's Jet Propulsion Laboratory maintain a constantly updated database of object trajectories. The system compares new measurements with previous predictions, calculating tiny corrections that improve the model of where the object will travel next. Those calculations are important because they allow observatories around the world to plan future observations. If scientists know where the object will appear in the sky months ahead of time, they can schedule telescope time long before the observation window arrives. And telescope time is extremely valuable. Large facilities like the Keck Observatory, the European Southern Observatory's Very Large Telescope, and even the James Webb Space Telescope operate on tightly scheduled observation calendars. Researchers must apply months in advance to secure observation slots. That is exactly what many teams are doing right now. Several research groups have already submitted proposals requesting dedicated observation time during the upcoming 2026 and 2027 viewing seasons. If those proposals are approved, astronomers will be able to study the object in greater detail than ever before. The reason those upcoming dates matter so much has to do with the geometry of the solar system. As Earth moves around the sun, our viewing angle toward distant objects constantly changes. Sometimes an object appears close to the sun in the sky, making it difficult to observe. At other times, it moves into darker regions of the night sky, where telescopes can capture longer exposures. According to orbital models refined using measurements from ATLAS and Pan-STARRS, the mysterious object will gradually move into a more favorable observation position in the coming months. That means astronomers will soon have a chance to gather clearer spectral data. Spectral data is one of the most powerful tools in modern astronomy. By splitting light into its component wavelengths, scientists can determine the chemical composition of distant objects. Every element absorbs and emits light in unique patterns, creating what scientists call spectral fingerprints. These fingerprints allow astronomers to identify materials that would otherwise remain invisible. For example, the Hubble Space Telescope has used ultraviolet spectroscopy to study the atmospheres of comets and distant planets. The Keck Observatory has detected molecules in the atmospheres of exoplanets using similar techniques. Now, those same methods are being used to examine the mysterious body that encountered 3I Atlas. Early spectral measurements suggest that the object's surface may contain complex organic compounds formed through long exposure to cosmic radiation. These compounds are sometimes found on objects in the outer solar system, especially those that have spent billions of years far from the sunday. But there is still uncertainty. One reason is that the object remains extremely faint. Even the largest telescopes can detect it only as a tiny point of light against the background of distant stars. That makes precise measurements difficult. Still, astronomers are making progress. Teams working with the Harvard-Smithsonian Center for Astrophysics are analyzing brightness variations that may reveal clues about the object's shape. When irregular objects rotate, their brightness changes slightly as different surfaces reflect sunlight. These changes create what scientists call a light curve. By studying the light curve carefully, astronomers can estimate how fast the object rotates and sometimes even infer its shape. Some early measurements suggest that the mysterious body might have an elongated structure rather than a perfectly round shape. Elongated objects are not unusual in space. Many asteroids have irregular shapes formed through collisions during the early history of the solar system. But if the object truly originated outside our solar system, its shape might reveal clues about how planetary systems form around other stars. Meanwhile, scientists are also examining the object's motion for signs of non-gravitational forces. In space, most objects move according to gravity alone, but certain processes can create additional forces that slightly alter an object's trajectory. One example is the outgassing effect seen in comets. When sunlight warms the surface of a comet, frozen gases beneath the surface begin to vaporize. As the gas escapes into space, it acts like a tiny rocket engine, pushing the comet slightly in the opposite direction. That is why comet orbits sometimes change over time. Astronomers carefully check for these effects when tracking objects like the mysterious body near 3I Atlas. So far, no clear signs of outgassing have been detected. If that observation holds true, it may suggest that the object lacks large amounts of volatile ice. That would make it more similar to an asteroid than a typical comet. However, another possibility exists. The surface might be covered by a thick crust of material created by radiation during its long journey through interstellar space. Such a crust could seal volatile materials beneath the surface, preventing them from escaping even when the object approaches the sunday. That scenario has been suggested before in studies of Oumuamua. Researchers analyzing data from the Hubble Space Telescope proposed that a hardened surface layer might have formed during its interstellar journey. If the mysterious object near 3I Atlas has a similar history, its surface may hide deeper layers containing frozen gases. Only future observations will reveal whether that idea is correct. And that brings astronomers back to the upcoming observation campaigns scheduled across several major facilities. The James Webb Space Telescope is expected to conduct additional infrared measurements during future observation cycles. Webb's instruments are capable of detecting subtle thermal signatures that reveal information about surface temperature and composition. If the object contains frozen methane, ammonia, or carbon dioxide beneath its surface, those molecules might appear in Webb's spectral data. At the same time, the European Southern Observatory is preparing follow-up observations using its powerful ground-based instruments. The Very Large Telescope in Chile has some of the most advanced spectrographs ever built. These instruments can detect faint chemical signals even from extremely distant objects. Together, these observations may finally reveal the composition of the mysterious body. And that information could answer one of the most important questions surrounding the encounter. Did the object originate in our own solar system, or did it come from another star system entirely? Tracing the origins of interstellar visitors is extremely difficult. Over millions of years, gravitational interactions with stars gradually alter the paths of wandering objects. But scientists can sometimes estimate likely regions of origin by analyzing the object's incoming direction and velocity. Preliminary calculations suggest that 3I Atlas entered the solar system from a region of the Milky Way located near the galactic plane. If the second object shares a similar incoming direction, it could mean both bodies originated from nearby regions of the galaxy. That possibility has sparked discussions among astronomers about whether the solar system might occasionally pass through streams of interstellar debris. These streams could contain fragments ejected from distant planetary systems long ago. If such streams exist, they might occasionally send multiple objects through our solar system within relatively short periods of time. Future surveys conducted by the European Observatory may help answer that question. Rubin's powerful sky survey will monitor the entire visible sky repeatedly, searching for moving objects and transient events. Some astronomers believe it could detect dozens of interstellar objects each year once full operations begin. If that prediction proves correct, events like the encounter between 3I Atlas and the mysterious body may become much easier to study. For now, however, the scientific community remains focused on the current investigation. The two travelers have already moved apart, continuing their silent journeys through space. But the information they left behind is still being examined. Every observation, every spectral measurement, every orbital calculation, all of it contributes to the growing understanding of what happened when a massive unknown object crossed the path of 3I Atlas. And as new data continues arriving from observatories around the world, the story of this strange encounter is far from finished. For months, the data continued to arrive quietly. Night after night, telescopes captured faint measurements of two objects slowly moving away from one another in the cold darkness beyond Neptune. At first, it seemed like the encounter was already over. The paths had crossed, the gravitational interaction had happened, and both travelers were continuing on their separate journeys through the outer solar system. But the real turning point came when astronomers began combining all the observations together. Measurements from the Atlas survey, spectral readings from the Keck Observatory, deep sky imaging from the European Southern Observatory, and infrared data collected by the James Webb Space Telescope were finally merged into a single refined model of the encounter. When the new model ran through the computers at NASA's Jet Propulsion Laboratory, the results surprised even the scientists running the simulations. The gravitational interaction had been stronger than expected. Not dangerous, not dramatic, but significant enough that the trajectory of 3I Atlas had shifted in a measurable way. That meant something important. The mysterious body that crossed its path had real mass. Enough mass to tug on a fast-moving interstellar traveler and change its route through the solar system. And once researchers estimated the possible mass range, they realized something even more interesting. The unknown object might be larger than many previously discovered interstellar visitors. Not a planet, not anything enormous, but possibly a massive rocky body that has been drifting through the galaxy for millions, maybe even billions of years. A silent traveler from another star system. A fragment of a distant planetary system that formed around a completely different sun somewhere else in the Milky Way. That idea changed how scientists began thinking about the event. Because instead of simply watching one interstellar object pass through our solar system, astronomers may have witnessed something far rarer. Two ancient objects from deep space crossing paths inside our solar system. The odds of that happening are incredibly small. Space is unimaginably vast. Objects traveling between stars rarely come close to anything at all. Yet, for a brief moment, far beyond the orbit of Neptune, gravity pulled these two travelers into a cosmic encounter. And humanity happened to be watching. Even more remarkable is the fact that this event occurred during a time when astronomy is entering a new era of discovery. With observatories like the European Observatory preparing to scan the sky continuously, scientists expect to detect many more interstellar objects in the coming years. What once seemed like rare cosmic visitors may soon become part of a much larger population of wandering debris from other star systems, each one carrying clues about distant worlds we may never see, each one telling a story about how planets form around other stars, and each one reminding us that our solar system is not an isolated island in space. It is part of a vast galaxy filled with moving objects, ancient fragments, and mysterious travelers crossing unimaginable distances. The encounter between 3I Atlas and this unknown body may only be the beginning. Future telescopes will discover more visitors, more encounters, more pieces of distant planetary systems drifting through our neighborhood. And each new discovery will bring us closer to understanding the larger story of how star systems form, evolve, and scatter their debris across the galaxy. For now, the two travelers have already moved on. Their brief meeting is over. But the scientific investigation will continue for years as astronomers analyze every detail of the data collected during this remarkable event. Because sometimes the universe reveals its secrets slowly, not through explosions or dramatic events, but through quiet interactions playing out across billions of kilometers of empty space. Moments like this remind us how much of the universe is still waiting to be understood, and how lucky we are to live in a time when our technology allows us to witness these events as they unfold. If you enjoyed this deep space investigation and want to keep following discoveries like this, take a moment to like the video and subscribe to the channel. Every like and every new subscriber helps this channel grow and allows us to keep producing more incredible space discoveries, deep space mysteries, and real astronomy stories from the universe around us. And if you want to see what scientists are discovering next about mysterious objects entering our solar system, watch the next video on your screen.